Recursion. Recursion is simply when a function calls itself. It can be an alternative to looping. For example, you have something like this. You create an array, you loop through, and print it. The recursive way to do this is this way. So we have a function print array, and then we call it, and then the input is array and the index. And basically what you do is you increment the index each time. So when you start, it'll be 0, then 1, then 2, and then we have this check. When it's higher than length, we return. So first we put in 0, so when it calls itself again, it will be plus 1. So say, for example, we start with 0. So 0 plus 1 is 1, 2, 3, and then all the way to 10. And when it gets to 10, it's above the length, so we break and we return. And then it basically returns from each function after that. So for looping, it is usually identical and usually longer to write and unnecessarily risky to use. There are some situations where recursion is the best option though. So one example is walking a directory. So say we do something like this. So we want to print all the files in nested directories. So we first start with the original path. We loop through all the entries. If it's a file, we print it. If it's a directory, then we call this function again and then look through all the files in that directory. And we repeat until none exist. This is also a lot safer because we're using an iterator and it can't really have a logic error in that situation. If you hate yourself, you can do it without recursion, which basically involves creating, kind of simulating recursion. So the reason why recursion works so well in this situation is you don't have to write the code again, and basically the input is what you use. So the input could nest. Whereas here we basically have to simulate it by creating a list. So we create a list that stores basically the root directories, and then we remove it every time we check it. So while the stack still has directories in it, we get the path, we remove that from the list, and then we loop through again, and then at the end, if it's a directory, we append it to the list. Basically, we're doing a lot of work just to not use recursion. So compare these two. Obviously, the one on the left is preferable in this situation. Chess engines are also another program where recursion is used very often. Let's see a Go example. Alright, apologize. Sorry. I had to write idiomatic Go here. It's extremely readable. I know. I think you'll agree. Let's actually fix that. Let's make this actually readable. So we put in the depth and the board, which is basically just a pointer to the situation on the board in the chess game. And what the perf function does is simply just plays every move in this position to a certain depth. So say you want to go 1 move, 2 moves, 3 moves ahead in the future. It plays all the moves, and when the depth is 0, it returns 1. We're just counting all the moves, is what we're doing. So we get the moves, we have the nodes, and then for every move, we make the move on the board, and then we call this function again. So basically, for this position, find every move. For those position, find every move. For those positions, find every move. And then when the depth is 0, return 1, and then return, and back to the original function, and then return the count. That's basically how it works. Let's replace depth with the actual number so we can see what's happening. So imagine we put in 4. So we start with 4, and of course 4 is not less than 0, so we continue. And then we go through the looping through all the moves, and we call perf. 4 minus 1 is 3, so we put in 3. 3 is not less than 0, so we continue. 3 minus 1 is 2. And then 1, and then 0. 0 is less than or equal to 0, so we return 1, and then return, and then return, and back to the original function. Let's do this iteratively in the same function and show you how painful this is. Sorry, again, idiomatic Go, right? It's such a great style guide. Let's actually fix that. So, perfect iterative. So we have to have, I had to extract a function, otherwise it wouldn't fit on the screen. So we have exactly the same as before, but we basically have a stack. We create a stack, which is a frame, and a frame just has the depth, the move index, and the list. So we're basically simulating recursion, really. So we create the stack, which will have every position inside it. And this is quite a lot more complicated. So we add the original position to the stack. We append that. While we loop through while the stack, isn't 0. We get the frame, we have to remove the last index from it. So we're looking at the last index every time. If the depth is reached, then we no plus plus and continue. Otherwise, we call this play move function on the right, which basically just increments the move index. It's kind of complicated, this. It's unnecessarily complicated doing all this. And you also have to have, when you're done in the original function, in perf to iterative, you have to make unmake move last. Not just unmake move, just unmake move last, the last move you played. So this is a lot more complicated. So which would you rather use? This, two functions, really complicated, or this? I think it's pretty obvious what answer you'll choose. So what are the downsides to recursion? So infinite recursion and stack overflows is the main one. So the biggest downside is when you mess up the check and loop forever. So for example, in the original example I showed you with print array, so there are ways to mess this up. So maybe you have the check wrong, or maybe you forget the check, maybe you infinitely loops. What if you do something like this, where you put index? What will that do if you just put index? Well, it will just print 1 forever and stack overflow. That's what it will do. It's similar to doing this. So you loop and then you don't increment I. It will just print 1 infinitely. There's also this problem. So on the left here, we go up and we're having an upward check. On the right here, we're going down and having a downward check, which could cause logic errors. So why is infinite recursion worse than an infinite loop? So that's how we have this, which is an infinite loop. It doesn't ever stop. And here, which is an infinite recursion, because we have the index, not index plus 1. So this just loops forever and won't crash. However, this loops forever and will crash. Why? So each time you call a function, a stack frame is created containing the return address, parameters, local variables, saved registers, and bookkeeping data. So you normally have a 1 megabyte, depends on the operating system, of memory per program by default, unless you ask for more. If you call a function millions of times in a row, you can run out of memory. This is called a stack overflow. So if you want to be really careful, you can add checks like this. So say, for example, we do this. Over max iterations, and have something like this. Over max iterations 1,000. And then if it's true, then you return and infinite recursion in print array. I shall show you what a stack overflow looks like. It's basically just going to print 1 over and over again, and then crash. So it prints 1, 1, 1, 1, 1, 1. And then it will say stack overflow exception, stack overflow. Let's see, we use too much memory. So you could, if you want, here's with the check. So now we put the check in over max iterations, and then put this in, and then it should catch it now. And then it says infinite loop here, so we've caught the error. So another downside is that complex code is harder to reason through and debug. Alright, here's an example from one of my compiler projects. So basically we're passing binary expression, which is basically something like, I'll show you on the right. So imagine we want to pass this, right? So we want to go 10 plus 10 multiplied by count minus 1. So basically we have to separate this into AST nodes. And the way it should look is something like this. So basically we have the declaration of value, which is an integer, and the assignment of the right is a binary expression of multiply of the binary expression of 10 plus 10 of the binary expression of count minus 1. That's what we need to do. And we basically have to recursively call it to do that. The problem with this is you can kind of forget because you're in the same function every time. So which AST node am I on? Was I on 10? Was I on 10? Was I on multiply? Which branch was I on? Was I on count? Was I on minus 1? And if you have a logic error in this, it can be very hard to reason about and very hard to debug. And especially if you use a breakpoint. Because you use a breakpoint, you go into one function, then you go back into the same function, you go back into the same function, you think, which part am I on? It's very hard to reason through. So in non-trivial examples, it can make things harder to debug. So recursion is a useful tool for certain situations like file systems, ASTs, XML JSON trees, chess engines, any nested data structure. But be careful, as infinite recursion and logic bugs are more likely.